About what really is flight mechanics, what are the objectives. So I discussed that we're going to do calculations like how far can an aircraft fly, how fast, how high, what's the optimum speed to have minimum fuel use. These kind of things are the things we like to calculate. And we saw that in order to do that, you need equations of motion. Does this work? You need equations of motion that describe how the aircraft is actually flying. So these equations of motion are basically Newton's laws applied to an aircraft. Now what we saw was that in these equations of motion there are basically three types of forces which are really relevant. That's basically the aircraft weight. You can imagine that a heavy aircraft might have less good performance than a light aircraft. There are propulsion forces, so thrust. We've looked at jet engines, propeller engines, and different propulsion types generate different thrust. But we've seen that propulsion is an important factor in the equations of motion. And finally, aerodynamics, of course, as well. Now, you've had several lectures about aerodynamics. All you really need in terms of aerodynamics for the flight mechanics lectures is basically one simple equation. So, not that much. But I do want to discuss aerodynamics a little bit, because so far you've been talking about lift coefficients, drag coefficients, and so on. But now we're dealing with a complete aircraft. We basically have to figure out what is the lift the aircraft can generate and what is the aerodynamic drag. So ideally I'd like to know, just like I've done with the thrust of a jet aircraft, we've seen that we can describe thrust as a function of airspeed. And I'm going to do more or less the same thing with aerodynamic drag. So let's have a look at aerodynamics. In the usual scenario of flight, when you're just cruising, constant altitude, no accelerations and so on, then we have lift is equal to the weight. Therefore, CL half rho V squared S must be equal to the weight. And we can also say that if you look at the lift equation, which must be the same as the weight to stay at a certain altitude, then we can also describe the equation for the airspeed. So you take out the airspeed and then you get an airspeed equation which depends on a couple of factors: aircraft weight, wing surface area, air density, and lift coefficient. But let's now just assume you have a given aircraft with a given weight and a given air density. That means that there's only really one variable in this equation, and that's the lift coefficient. Now, you should know this graph over here, that lift coefficient, or this one over here, lift coefficient is basically a function of the angle of attack. So the angle that the aircraft makes with the oncoming flow. So if you basically, if you have a large airspeed and we consider the same weight, surface area and air density, then in order to stay in the air, the lift coefficient can be small. Similarly, if you have a small airspeed, then again you must create the same amount of lift to stay in the air, because the aircraft weight is given. Then you should have a high lift coefficient. So that means that if you're flying slowly, and I'm exaggerating this picture a bit, but if you're flying horizontally with a small speed, then the nose of the aircraft should have quite a large angle with respect to the oncoming airflow. So the angle of attack at low speeds is high, and if you fly very fast, then, so we have a large speed here, then this angle of attack is quite small. So that's the only thing you should really understand. Flying slowly, you need a high angle of attack. Flying fast, you need a low one. Is there a question?
Yes, in the graph on the upper right, shouldn't it be the other way around? I mean, three-dimensional flow has less lift, right?
Is it okay if I come back to that a little bit later? It's not so relevant for this story really, but I'll come back to that later. So what we know now is we need to fly at high angles of attack at low speeds and at low angles of attack at high speeds. And what you see as well, just to remind you, is that the aircraft isn't following its nose. The airspeed vector is in a different direction than the actual nose of the aircraft. So this also means that if you want to fly as slow as you can, so at minimum airspeed, then you must make this lift coefficient as high as you can. Now you know, as you start increasing the angle of attack, then at some point you may have separation. So your lift coefficient will increase with angle of attack, and at some point the lift will suddenly diminish because the flow simply can't follow the profile. So there are different devices that were designed basically to improve this behavior, because if you start to go to an airfield and you want to land or take off, then it's actually nice if you can fly slowly, because that means you only need a limited amount of runway, and that's also a performance parameter of an aircraft. Also, in other words, if you have a given runway, it means if your CL max is high, then you can actually take more weight on board. So that's quite an important thing. And there are different devices. You can imagine devices at the front, at the leading edge of the profile, that may help the aerodynamics to stay attached to the airfoil. And if you do that, then CL max for the original case would be approximately this, and CL max for the case where you've opened this slot maybe a bit higher. So that helps you a lot. Other things that can help you, let me see. These will come later, but you can imagine, I have some other pictures later on that will show you that you can also have devices at the trailing edge which you deflect in order to create a more curved profile, and those will also help you, and those will shift this whole curve upwards. So that will also help you to improve maximum lift coefficient. But now what we're basically interested in is an aircraft. I'm not interested in just a two-dimensional profile. I'm talking about real aircraft, so three-dimensional aircraft. And what you see here is basically an aircraft from the back flying along. And what's important to realize is that if you look at the back, then there's a relatively low pressure on the top of the wing and a relatively high pressure on the bottom of the wing. Now, since the wing is only finite, this means that the air at the tips will start to form vortices. Of course, at the tips, the air would like to go in this direction from high pressure to low pressure, which means there are these vortices trailing the aircraft. And there are many different ways at which you can look at this picture, but what I think is most easy to understand is that if you leave these vortices in the air, then once an aircraft has passed, a lot of air is still moving around like this. And that means a lot of energy has been dissipated into the air. So that means that you basically lose energy just due to the fact that the aircraft is not a two-dimensional thing, but a three-dimensional thing. So these are some pictures where you can actually see those vortices in flight from a wind tunnel, but also from actual aircraft flying around. And what you then have learned in the aerodynamics lectures, I presume, is that the drag coefficient depends on two things. It depends on some kind of a constant factor, which we call the zero lift drag coefficient. And secondly, there's a factor here which depends on the lift coefficient. Now, as I just shown you in this picture, as soon as you start creating lift on a wing, then there will be a pressure difference between the, does it still work? Between the top and the bottom. So as soon as you start creating lift, then you'll start losing energy in the atmosphere due to these vortices, and therefore you create drag. So there's a second term in this equation which states that part of the drag coefficient depends actually on the lift coefficient itself. So this is what we call the induced drag coefficient. So there are some additional parameters, but you can see it's a function of CL squared and some other ones, pi, A, and E. Now pi, of course you know. A is basically the aspect ratio of the wing. So that's a constant factor. It's just a geometrical thing telling you how large is the surface area of the wing and how wide is it. And finally, E, that's what we call the Oswald factor. This is basically a factor which tells you how good the wing is. It goes from 0 to 1, and the better you've designed it, basically, the better you have a lift distribution along the wing, the better this Oswald factor E will be. So we have this parabolic drag polar. I call it parabolic because it's a parabolic function with a squared. And this is basically the only equation you need to know from aerodynamics to solve flight mechanics questions. Now this is all very nice, but let's look at it a little bit more closely. If you consider aerodynamic drag as a function of lift coefficient, then you can basically draw this equation. So if we look at this curve on the left, then if you would only have a two-dimensional profile, then of course, if you look to this line on the left, then for different angles of attack or for different lift coefficients, because CL is of course a function of angle of attack, you more or less have a certain drag coefficient. So this is just two-dimensional, what we call profile drag, because this profile, this airfoil creates drag. Now at high lift coefficients, somewhere over here, it means you're near this stall region, and then these curves start to change a bit. Now that's a two-dimensional lift relation between lift and drag. But of course, I've just discussed that there's also a three-dimensional factor, that as soon as we start creating lift, we start losing energy in the atmosphere, and therefore aerodynamic drag increases. So if you just look purely at the wing, then if you don't create lift, so if we we're on the x-axis here, then the drag would be the same as the two-dimensional case. But as soon as we start creating lift, then we'll have more drag than the two-dimensional case. And therefore we call this the induced drag coefficient. So we had profile drag and induced drag. So that gives you a parabolic relation. But there's one thing you should not forget. An aircraft is not just a wing. You have a fuselage with passengers inside. There are all kinds of things sticking out, like landing gears, antennas, and so on. So if you look on the, at the whole aircraft, then the actual drag lift relationship looks the same, but the whole curve has shifted to the right, simply due to the fact that there are all kinds of elements which also create drag, like a landing gear, antennas, fuselage, and so on. So this formula here is basically a representation of that curve. Because if you would take this curve and you would plot it a little bit differently, so now I have CD on the y-axis and CL squared on the x-axis. So I make exactly the same plot as on the left-hand side. I'm just turning it around and using a squared. Then I can see that the curve, so the not dashed line, is almost completely straight. If I draw a line through that, so a straight line, then that's, it's a bit of a stupid thing. The straight line is almost the same as the curve for the complete aircraft. And this basically shows us, you could do this for many different types of aircraft, you would always see more or less the same plot. This basically tells us that this parabolic equation is actually correct. It's really good. Up until very high lift coefficients, it's almost spot on. It's just that once you've reached this portion of the lift coefficient where stall starts to occur, then it's not such a good equation anymore. But you have to realize that in normal flight, you will always have a speed which is higher than the stall speed, so that's not really relevant. So this equation is really a good equation. And it's actually quite nice because I've just taken a picture of one of my master students, of his work then, of course. This is just some kind of an aircraft that's being researched. Now, just to tell you the background, it's a closed wing system. So basically the tips of those two big wings, they're joined. And the idea is that then by doing that, you don't get that many vortices at the tips of the wings. But leaving that aside, creating such a picture, or doing the calculations, because these are all the pressure distributions over the aircraft. So these are aerodynamic calculations. Doing these calculations took the student a couple of weeks to prepare the program, to do let it run, to get good results, and so on. So you do all these calculations, takes you weeks, and then by the end of it, if you compare your results, and you would try to catch them in one equation, then you can just make one simple parabolic equation from it that represents this really well. So that's quite interesting, that you end up with a really simple formula that is actually really accurate. So, like I said, this is a drag coefficient, but I'm not interested in a drag coefficient. I'm interested in real drag, real aerodynamic drag, because we're looking at a real complete aircraft. So let's just see. So my objective now, and that's to finalize the whole aerodynamic story, I want to know what happens to the aerodynamic drag as a function of airspeed. That's all I want to know. Now, what you see here, on the left-hand side, all I'm saying, if you fly horizontally, constant speed, then we have lift is equal to weight. You've just seen this picture before. So, before I took airspeed out of the equation, you can also say, well, let's take lift coefficient to the left-hand side of the equation and see what that is a function of. So, lift coefficient is a function of aircraft weight, wing surface area, air density, and airspeed. So again, high airspeed means a small lift coefficient, low airspeed means a high lift coefficient. Now this is a given. If you have a certain airspeed, you need a certain lift coefficient to stay in the air. But now let's have a look at the drag. We've just gotten this relationship, so the aerodynamic lift drag polar, which says there are two portions to the drag. There's this zero lift drag coefficient, and there's this induced drag. Now, just to remind you, this term and pi and a and e, they're all constants for a given aircraft. Now we're interested in actual drag. So actual drag is drag coefficient half rho v squared s, just like for the actual lift. And if we take that equation, then we can fill in the equation we already have for the drag coefficient. If you do that, you end up with this. So I've just taken the top equation, filled it in here, and now I get two portions to the drag relation. So I have CD0, half rho v squared s, and I have this funny factor CL squared times half rho v squared s. Now, we already know that for a given airspeed, we need a certain lift coefficient. So we already have a relationship for the lift coefficient. And let's just take that equation on the left and put it into the equation on the right. Now, if you do that, then this is what you end up with. Now, you don't have to derive this yourself, just see what happens. The important thing to notice is that if you take CL squared, and if I take this thing here squared, I have airspeed squared on the bottom of the equation. So that means that squared, I get airspeed to the power 4, and I have to multiply that with half rho v squared s. So these v squareds, you can get rid of them, more or less, or you get rid of two of them, and this is the final equation you get. So it's a very simple derivation. You just fill in the parabolic lift-drag polar in the lift and drag relations. But this is then what you end up with. And what you have to see is that there's one part here on the left which depends on v squared. And there's one part here on the right which depends on 1 over v squared. So that means that if I take the left-hand side, let's call that number 1, if I would just plot drag as a function of airspeed, then that curve number 1 looks more or less like this. It's just a parabolic curve. It's a function of v squared. The other one, on the other hand, has all constants in there, but it's 1 over v squared. So if I call this one number 2, then number 2 looks a bit like this. So 1 plus 2 gives you the total drag, So the real drag looks something like this. Now, of course, people have made better pictures than I have. But this is what it more or less looks like. So the actual drag curve is basically a parabolic relation. And it's quite interesting when you think about it. If you think about that, if you fly very slowly, you have a certain drag. And then if you start to increase the speed of the aircraft, then the aerodynamic drag is actually reducing. So that means that at some point you will have a minimum drag, and after that point the drag starts to increase again. So if you look closely at the picture, then we have this induced drag term, we have this zero lift drag term. Then on the left hand side of the picture, you see that it's working now, isn't it? Can you hear me like this? Okay. You see that on the left hand side, basically induced drag is important, and on the other side the zero lift drag is important. And this is because at low speeds you have to fly at high lift coefficient, therefore you get a lot of these vortices at the wingtips, and at high speeds the aircraft is flying at low lift coefficients, so it mainly becomes friction drag on the aircraft. But it's interesting to see, because this is one of the only vehicles I'm aware of that shows this behavior. So high drag at low speeds, and then drag reduces. So that's quite interesting. If you look at cars, trains, whatever, none of these vehicles show that type of behavior. Now that has some important consequences, because if you look at these equations, then you see, if let's just consider you were trying to design an aircraft for high speed flight or for low speed flight, then at high speed zero lift drag is important, and at low speed induced drag is important. So at high speed there's only one variable, and that's CD0, that's important, whereas at low speed you see that wing surface area is on the bottom, aspect ratio is over here. So if you look at aircraft, then it's actually on the right hand side you see a starfighter, so that's an aircraft that can fly about Mach 2, so it goes very fast, and that means that aircraft only needs very small wings, because you're going fast anyway to create lift, so you have dynamic pressure to create lift. And if you would make a cross section of the wings, so you'd cut the wings in two and have a look, then it looks a bit like this. So these are very sharpish, thin wings that have very low friction drag. Whereas if you look at this other aircraft, which was a bicycle plane, so there's one guy pedaling in the front. You need to be quite fit to do that, because you need to generate a lot of power. But you can imagine if you cycle yourself, you can't generate a lot of propulsive force, so you have to fly slowly. Now, in that case, this other type of drag, which is induced drag, becomes really important. So there you see that this aircraft on the left has a completely other wing. The wing itself is designed completely differently. And that's simply because of all these terms you see in this induced drag relation. So aspect ratio, Oswald factor, they all play an important role. An aspect ratio was b squared over s. So if you have very long, thin wings, then you have a large aspect ratio, and that's what you basically see here, long, slender wings. So that's aerodynamic forces, and we've ended up with the aerodynamics as a function of airspeed. So if I then summarize this first lecture, which I wasn't able to finish, then we've seen that we could derive two equations of motion based on Newton's laws. We've seen that thrust of a jet aircraft or power of a propeller aircraft, we can assume that they are more or less constant as a function of airspeed. So we can say, well, thrust of a jet aircraft as a function of airspeed is more or less constant. And we can say basically the power of a propeller aircraft is more or less constant. And we have now an equation for the aerodynamics, which told us that aerodynamic drag as a function of airspeed looks more or less like that. So that's all we now need to start solving actual questions. So then let me see if you want to keep these notations? Yes? No? So that was the main introduction. We have all the ingredients now to start solving questions. And as I said in the previous lecture, this is what I'm going to talk about. So I'm going to talk about introduction. Then I'm going to look at horizontal flight performance. So what is the performance of an aircraft if it stays at one altitude? Then climbing flight, descending flight. And then we're going to combine everything into a flight envelope describing what an aircraft can actually do as a function of airspeed. So let's start with the introduction. And this is about horizontal flight performance. So the questions I'm going to ask: how fast can an aircraft fly? How slow can it fly? Now that's something we've already covered basically. And more importantly is actually at what speed should you fly to be able to fly as far as you can. So this is important in terms of fuel use. So that's relevant for airliners if they want to fly from A to B. They want to have minimum fuel consumption. So that's just an economic thing. And another thing I'm going to look at is at what speed should you fly to stay in the air for as long as you can. Now that's a little bit, it's related to the one before that, but it's a little bit different. So sometimes you have these military aircraft in the sky that are just circling around to maybe monitor the airspace. In that case, you're not interested in flying from A to B, you're just interested in staying up there as long as you can with the fuel that you have on board. So that's another thing we're going to look at. The material you need to learn is covered in Anderson as well. So these are the paragraphs if you want to read a bit more at home. But let's quickly look at the equations of motion for horizontal flight. So the type of flight for cruise, maximum speed, minimum speed, and so on. So basically what I'm going to do is I'm going to take these equations of motion and I'm going to simplify them to the case that is relevant now. So just to refresh your memory, you've seen this picture before, but every exam you have to derive it. You need it for every question basically that we solve. So just to refresh your mind, I will show you that basically you can derive the general equations of motion. So F is m times A. With a free body diagram and a kinetic diagram. Now, if you have an aircraft on the left, and we start looking at the free body diagram first, then you have to define some axis systems. So there's a moving Earth axis system, which has the same orientation as the Earth, and is fixed to the aircraft. Then there's also something we call a body axis system, fixed to the plane, because the difference between these two axis systems tells us what is the orientation of the aircraft in space. Now the difference between the two is the angle theta, which is called the pitch attitude, and that is what the pilot actually sees when he looks outside the window of the aircraft. Now the aircraft isn't following its nose, so you have a certain airspeed, and that is in a different direction than the nose of the aircraft. But the airspeed vector, of course, is very important, because this one determines where you're going, and that is very relevant from a performance point of view. We can also define an angle between the horizon and this airspeed vector. So angle gamma, the flight path angle, and that simply tells us how steep we are climbing or how gradual we're descending. Now, finally, there's an angle between the aircraft and the airflow, and that of course is the angle of attack, which is relevant for the aerodynamics, and that tells you how much lift and drag the aircraft will generate. So, based on this, you can describe several forces. Lift being perpendicular to the airspeed by definition. Aerodynamic drag, which is parallel to the airspeed vector, but in the opposite direction, of course. Aircraft weight, and finally there's a thrust vector, and the thrust vector will be fixed to the plane depending on how you position the engines. So the thrust vector will also have some kind of an angle of attack. Now, if you look at the kinetic diagram, this is basically the accelerations of the aircraft. Then we have the same axis systems, same airspeed, but now let's introduce two accelerations, because the plane can move in a two-dimensional plane. So, just by definition, I'm taking the accelerations parallel and perpendicular to the airspeed. So the aircraft might be accelerating, hence you have airspeed with time varying, so the horizontal or the component parallel to the airspeed. And there may be a vertical acceleration, which you probably know as mv squared over r. Okay, it's working again. mv squared over r. And in the previous lecture I showed you that you can also describe it a little bit different as m times v times the change of flight path angle with time. And the only reason we write it like that, it's exactly the same as mv squared over r. That's because a radius in a pull-up doesn't mean that much. It's a radius to a virtual point in space, whereas we already have a flight path angle which is relevant for the forces, so that leaves us with less variables. So this was a bit quickly, but I've already shown it. You have to be able to draw these diagrams and to derive these two equations of motion. So if you take the forces parallel to the airspeed and the forces perpendicular to the airspeed, and you equate them to m times the acceleration, then these are the two equations of motion that you end up with. So this is general, so climbing, descending, accelerating flight, but now we're going to look at a flight condition where the aircraft is performing a horizontal and steady flight. I put those words bold simply because these statements are statements you will get on the exam. For example, the aircraft is flying horizontally, and then you must know what horizontal exactly means. So these are 4 definitions. They are fairly easy to understand, but you have to know what they are. So if you look at horizontal flight, then of course that means you're staying at one altitude. So this flight path angle, if you look at the picture, the angle of the airspeed with the horizon in horizontal flight, of course, is equal to 0. So horizontal flight, the third one, means flight path angle is equal to 0. Steady flight, as steady as the word says, means that basically forces and moments acting on the aircraft don't vary in time, not in magnitude, so the size of the force, or in the direction. Now, all that means in simple terms is basically that the aircraft is not accelerating or decelerating. Because if you were accelerating, then either lift or drag would have to change. So steady flight just means you're flying at a constant speed. Straight flight, that's maybe a little bit different than horizontal flight, but I've just described that airspeed is defined as the flight path angle is defined as the angle between airspeed and the horizon. So straight flight just means you're going in a straight line. So the airspeed vector isn't changing direction, which means that gamma may have a value. You might be climbing or descending, but gamma is constant. So the change of flight path angle with time is 0. Now, final one, symmetric flight, is not so relevant for this lecture really. All it means that the aircraft is not turning. There's one additional thing, and that says that the plane of symmetry of the aircraft is perpendicular to the Earth. Now that is maybe a bit difficult to understand directly, but what do I mean with that? If you have an aircraft, you could actually fly such that if the pilot puts in a pedal input and the rudder of the plane will deflect, then you can actually fly a bit sideways. And you can imagine if you fly a little bit sideways, then that's not something you would call symmetric. So that will be the case. Don't look all the angles, etc. But that will be the case on the left-hand side, for example, if you have an engine failure. If one of the engine fails, then the other one has to provide all the propulsive force. So that means you get a moment around the aircraft center, and the aircraft nose will have to go to the left or the right. And you have to compensate for that with a rudder input. But clearly, even though you can fly with an engine failure, it's not something you would call symmetric. Now, fortunately, that doesn't happen that much. But what does happen a lot is that you have to land on an airfield, but there will be side wind. So the airfield will have a certain direction, but there may be side wind. In order to fly and to land on the airport, you basically have to point the nose of the aircraft into the wind. So you're kind of flying sideways to get rid of this wind component in order to land straight on the runway. So that means you would approach the runway like this on the top hand picture. But of course, if you put it on the ground, then the wheels would not be in the same direction as the runway. So just before you land, you will put the nose in the direction of the runway. You'd have to bank the aircraft as well. You'd land on one wheel and then you put the other wheel on the ground and you've landed. Now, these two pictures show you in general how that works. But let me just show you one video before the break of maybe an interesting plane. Hope it works. This is a B-52 landing. Now, as you may know, a B-52 is a rather large airplane. And if this plane was to land like this, so with one wing down, the wings are so long that the wings would hit the ground. So this plane can't do that. So this is one of the only aircraft that is able to change the direction of the landing gear. So you can see it's actually landing a bit sideways. And as the picture goes on, you'll see better. But you see the aircraft is on the ground. You can see by the direction of the parachute where the wind is coming from. And it's more or less driving sideways, simply due to the landing gear, which can be directed in the correct direction. So that's side slip. And you can see it's driving sideways. And that means that these equations, if you consider horizontal and steady flight, will simplify, but how they will simplify, I will tell you after the break. Flying at one altitude, at a constant speed, and we're not doing any turns. Now we had the equations of motion, but we know horizontal flight means flight path angle is 0, because it's the angle with horizon and airspeed. Steady means there's no change of airspeed. And finally, symmetric just means we don't have any turns. But that also means that we only have 2 equations, because this is 2-dimensional flight instead of 3. So if you say, well, gamma is 0 and dv dt is 0, and just out of convenience, to make your life a bit easier, I say, okay, the angle of attack of the thrust is almost 0, so let's say the thrust is more or less pointing in the same direction as the airspeed, then these equations become a lot simpler. So cosine of alpha t becomes 1, the sine of gamma becomes 0, dv dt becomes 0. We don't have a change of flight path angle with time. Nope. So since gamma is 0, that term is also 0. The cosine of gamma is 1, and the sine of alpha t is 0. So that means that these complicated equations, which you will need later on, for this scenario, they just become thrust equal to drag, and lift is equal to weight. So that's very simple. Equations you already know. The most simple form of the equations of motion. And the question is, we have these 3 forces, and how do they actually vary with airspeed? Because then we can say something about the performance of an aircraft. Now we've already derived that basically. We know how aerodynamic drag behaves, we know how thrust behaves as airspeed. So what we can now make is a diagram where you have both the aerodynamics and the propulsion together in one diagram to tell you something about performance, and this is why we call it a performance diagram. And that diagram will help you to solve basically all the performance questions, so minimum airspeed up to speed, instability, range, endurance. So everything can be solved basically with a simple diagram. And the performance diagram, you also see it sometimes, it's called a Pernod diagram, but all it means is if you just take a certain aircraft with a certain altitude, a certain engine setting, certain aircraft weight, and then we're going to plot thrust and drag in one diagram. And that looks more or less like this. So you can plot a force as a function of velocity. So here we have that aerodynamic drag that we just described for an aircraft. The thrust, here I'm talking about a jet aircraft, and we discussed in the previous lecture that for a jet aircraft, if you keep everything the same, so the throttle setting, and you just vary airspeed, then the thrust of the engine won't really be affected. It will be more or less constant. So this is typically what a performance diagram looks like. Now, here I have force. You could also decide to draw it as a function of power. So you may remember from last week that, or from the previous lecture, that power available, so basically the power you need to fly from A to B, power available was the thrust multiplied with the velocity. So if you have a diagram with forces, you could also say, well, if I multiply thrust with velocity, then I can also plot power. So aerodynamic drag multiplied with velocity is what we call power required. So then if you would draw it as a function of power, so power versus airspeed, then all you do is you take this aerodynamic drag curve multiplied with airspeed, then it gets tilted a little bit, but you get a curve with more or less the same shape on the right hand side. So performance diagram shows you propulsion and aerodynamics in one diagram, and the difference between the two tells you what the performance is. You can imagine if at a certain airspeed you have much more thrust available than you really need in terms of aerodynamic drag, then you can accelerate very rapidly, or you can climb very quickly. So this can tell you a lot of things about the aircraft performance. Now here, this is just as an example, the actual performance diagram of a real aircraft. So this is actual aircraft data, and this is just to show you that this is these curves, like the aerodynamic drag curve, it really looks like this parabolic relation. In this case, it's not a pure jet aircraft, it's maybe a little bit of a different engine, so you have a different behavior of the thrust with airspeed, but this is just to show you an actual performance diagram of a real aircraft. Now, to summarize, so far we've derived that aerodynamic drag as a function of airspeed is this parabolic relation, and we say for a jet aircraft thrust is more or less constant, and for a propeller aircraft power is more or less constant. Is there a question there?
Yeah, in the previous two graphs, the performance graphs, since power is the force times the speed, what was the integration for the other two previous two? Yeah.
Sorry?
Integration mean for the graph between graph and graph. Would it have any meaning?
Which one? The one on the left or the right? Well, the difference between thrust and drag is basically a force difference. So if you would consider, let's say you fly at this velocity and the drag is this much, and this is the thrust you can generate if you give full power, then this difference is a force difference, and that tells you basically F is m times a, how fast you can accelerate. So both diagrams, they're related to each other. Basically, one is just another way of showing power, the other one shows force, but they give you the same information more or less. But I will show you that in some cases it's nicer to look at power, and in other cases it's nicer to look at forces. But you can use both. Doesn't really matter which one you use. If you have one of these diagrams for an aircraft, you can solve all the performance questions. So, back to this diagram. Now I said for a propeller aircraft, that was an aircraft that could adjust the pitch of the propeller blades in order to get optimal efficiency as a function of airspeed. So this is why we assumed power was more or less constant for a propeller. And just to show you, if thrust of a jet is constant, then if you'd say power available is thrust multiplied with velocity, then the power curve of a jet looks like a straight line from the origin in a power diagram. So this is what you would call a performance diagram, and we're going to use this diagram basically for all these applications, minimum airspeed, maximum airspeed, range, endurance, and so on. So let's start with minimum airspeed, or with horizontal flight performance. So we're going to look at minimum airspeed, how slow can you fly, maximum, how fast. Range means the distance you can fly with an aircraft. Endurance, how long can you fly. And then there's a special thing called speed, stability, and instability. And that means in certain portions of a flight, if the pilot is just drinking coffee, then the aircraft will start to accelerate or decelerate. So meaning it's not stable, and the pilot would have to actively control the aircraft to stay at a certain speed. How that works I come back to later, but you'll also see that there are also certain portions of flight where the aircraft is stable. So the pilot could go have a coffee, go to the toilet, and the plane would just fly at a constant speed. Now that's an important thing to be aware of as a pilot, and it's fairly easy to solve with our equations of motion. Now, like I said, we're considering horizontal, steady, symmetric flight. So lift is equal to weight, and thrust is equal to drag. And in other words, since power is a force times a velocity, thrust equal to drag also means that thrust times velocity equals drag times velocity. So power available, the power you have from the engine to transport yourself, is equal to the power you require to overcome the aerodynamic drag. So that's the same equation basically. Now, minimum airspeed. That's one we've already more or less solved. And that reminds me, I didn't answer your question earlier on about the curve. Is it okay if I answer it at the end? Because I don't have that much time actually. I'm already an hour behind. So we have lift is equal to weight. CL half rho V squared S equal to weight. So we have an equation for the airspeed if lift is equal to weight. So you've seen this before. Minimum airspeed you will obtain when lift coefficient is maximum. So you need a high angle of attack to create the most lift you can. And this picture here is a nice example. So what you can see there is the aircraft is actually quite steep. It's flying horizontally, and you can see from all the flow around the wing that the aircraft is actually in a more or less stalled condition. Now this aircraft is basically cheating because it's an aerobatic aircraft, and this propeller can create a lot of thrust. So this means it's more or less hanging on its propeller. Now, normal aircraft have a thrust which which may be in the order of 25% of the aircraft weight, whereas such an aerobatic aircraft can generate much more thrust. So normal aircraft wouldn't be able to do it, but this one can, and it's quite nice to see that you have then separated flow around the wings. So various devices that can improve maximum lift coefficient. You might have a device at the leading edge of the wing, which we call a slat. And if you open that, you increase CL max. Similarly, at the trailing edge of the wing, we have what we call flaps. So these are what we also call high lift devices. And if you deflect something at the trailing edge of a wing, then you increase the curvature of the profile, and therefore you also create more lift. Another thing you're doing is that these flaps, they basically come out of the wing, so they also increase the wing surface area, which also helps to create more lift. Now there are various options to do this. You can have a very simple flap, a plain flap, up to very complex systems. So this is what you call a triple slotted flap. So it's a flap which consists of 3 parts which are all mechanically linked to each other. And you can imagine that the one on the right, that works most efficiently from an aerodynamic point of view. There is, however, a difference. Maybe with the simple flap on the left, you get less lift coefficient, but the advantage is that the whole system itself, it weighs much less than this complex system. So if you look, for example, at a Boeing 747, which is a heavy aircraft, it has a very complicated triple slotted flap system, which is very heavy, it's very expensive, difficult to maintain, and that gives you good performance. But if you look back at this equation, then the minimum airspeed also depends on aircraft weight. So if you're heavier, so you have a heavy flap system, then that is disadvantage. So what you see nowadays is that most aircraft are now designed actually with simpler flap systems, simply because they're easier to maintain, easier to make, cheaper to make, and at the end of the day you get the same performance. Now if we then go back to our performance diagram, if you have the aerodynamic drag curve, then the minimum airspeed is simply the airspeed where the curve stops. Okay? Each point on this curve is related to a certain angle of attack. So you have a small angle of attack here and a high angle of attack there. And at some point, angle of attack becomes so large that you get separated flow. And that's where we stop drawing the curve, because you can't fly there anymore. Now this is an example calculation. It's not so difficult. This is something we could ask you to do on the exam. Given some kind of an aircraft with a certain wing loading is weight divided by wing surface area, and a certain maximum lift coefficient, then have a look at which airspeed does stall occur. And we do that for 2 scenarios, one at sea level and one at 5 kilometers altitude. Now the answer, of course, you always have to show what is the equation for minimum airspeed, and you can simply derive that from lift is equal to weight. If you then fill in the numbers, now that's pretty straightforward. I'm sure you'll be able to do that. And you see minimum airspeed at sea level is 50 meters per second, and at higher level, 5 kilometers, it's actually almost 70 meters per second. So that's pretty interesting to see. So if you start flying higher, you also have to fly, the minimum airspeed at which you can fly is also higher, simply because the air is less dense and you need to go quicker to create enough lift. Then, one new one, maximum airspeed. That's of course how fast can you actually fly with an aircraft. And let's just apply this to a jet aircraft. So I have this performance diagram with aerodynamic drag, and I've drawn a straight line which is for the maximum thrust this jet aircraft can generate. And you can already imagine that if you want to fly fast, you have to create as much thrust as you can. Now, if you want to find the maximum airspeed, it's actually, in this diagram, it's really straightforward. Because over here in this purple point, you can see thrust is equal to drag. And if you would try to fly faster, then maybe drag would be over here, but that would be larger. The drag would be larger than the maximum thrust you can make, so it's impossible to fly there. So you find the maximum airspeed simply by saying maximum thrust must be equal to drag, and then I have my maximum airspeed. So that's pretty simple, but of course you would also like to be able, in a diagram you can just draw it, but you would also like to be able to actually calculate it. So how do you do that? Now we have our equations, because we're flying at a constant speed, constant altitude, thrust equal to drag, lift equal to weight. So maximum thrust must now be equal to the drag. So what we can also say, by the way, you can arrive at the final answer in many different ways, but this is just a trick to do it a bit faster. So maximum thrust is drag. So you can also say, well, that's actually drag multiplied with 1, lift divided by lift. Now, since lift is equal to weight, you can also say, well, that's weight divided by lift. So then you get maximum thrust is drag divided by lift multiplied with the weight. And that's the same as saying that's the drag coefficient divided by the lift coefficient multiplied with the weight. Now, we have this relation, this parabolic relation for the lift-drag polar. Usually you'd write it like this. But for now I said, well, this 1 over pi AE, those are all constants, so I just call them k to make it a bit simple. So I have CD is CD0 plus k times CL squared, where CD0 and k, they are given constants for a given aircraft. Now, the maximum thrust is a function of drag coefficient and lift coefficient, but you can see now that drag coefficient is in fact a function of the lift coefficient. So if you would take this equation and put it in there, and I take this weight and I put it on the other side of the equation, then I end up with this relation. So maximum thrust divided by weight is basically a function of lift coefficient. Because the other terms, they're constants. If I take maximum thrust over weight, to the left-hand side I get this. And from this you should see that now I have one equation with one unknown, which is lift coefficient. Since maximum thrust is given for an aircraft, the weight is given, factor k and CD0, they're all constants. So this is basically ax squared plus bx plus c is equal to 0. And from that you can actually calculate CL, which is a certain number for a given aircraft. And if you know the lift coefficient, then from lift being equal to weight, you can also calculate, okay, what is then the actual airspeed? Just fill it in there, and you know what the maximum airspeed of the aircraft is. Now this is all theory, of course. So I have one example with actual numbers for an actual aircraft to show you how it works in real life. Is there a question? Yeah, that's right. Yeah, you get two answers, but you will see straight away that one of the two answers will not make sense. But I'll show you that probably in the next example. Typically you would get one very large CL and a very small one. And of course, the small CL is the one related to a small angle of attack, so that's where you fly fast. So the other one is basically, the other solution is probably where this curve intersects there. And that would be then, it's not the minimum airspeed, because it might actually be below the minimum airspeed, but that's also a mathematical solution. So let's just take this aircraft, the aircraft of the faculty, and let's see what is in fact the maximum airspeed when it's flying at sea level, at a certain aircraft weight, when it's fully loaded with passengers and so on. Now this aircraft can generate 12 kilonewtons of thrust, so that's both engines combined. And we have some parameters for this aerodynamic drag. So a zero lift drag coefficient of 0.02 and a maximum lift coefficient. This aircraft has high lift devices that has some flaps at the back of 1.35. So let's just see how do we calculate maximum airspeed for this aircraft. Works as follows. You always have to state, okay, what's happening, so this is how you would write it down in an exam. What's happening at maximum airspeed? Lift equal to weight, thrust equal to drag, and we have relations for lift and drag. I don't know if it's readable from the back, but we know thrust is equal to drag, which is CD over CL times the weight. So if we take that, you can also say, well, weight divided by thrust is equal to CL over CD. So that means we have an aircraft weight of 60,000 newtons, 12,000 newtons of thrust. So CL over CD must be equal to 5 to fly in this maximum condition, because 12 kilonewtons is the maximum thrust. So CD is CL divided by 5. And I have a lift drag polar, so that means this is CL divided by 5. So if I rewrite it, I take CL over 5 to the left hand side, then I get this equation with CL squared in there being equal to 0. Now if you fill in all the numbers, you just get x squared plus bx plus c is equal to 0. You have the numbers here. And then you find CL is 0.11, and probably if you type it in your calculator, you will also find some large value of CL. But of course, the low value of CL is the realistic solution. Now this is just a lift coefficient. So airspeed follows from the airspeed equation, and that's about 170 meters per second. So that's pretty fast at sea level. Now, just for your information, what is then the Mach number? Perhaps interesting to see. At sea level, you can fly, or the speed of sound is 340 meters per second. So that means that if you take this maximum airspeed we just calculated, you can say, well, that's actually Mach 0.5. So that's pretty fast, but it's by no means high subsonic or even transonic. So that's the minimum airspeed, maximum airspeed. Now let's start having a look at range. So trying to fly as far as you can. So there are two questions you could try to do. You could say, I take my aircraft, I want to fly as far as I can. Just see where do I end up. Okay? Now that's not a really normal way of flying. Normally speaking, you would say, I want to fly from Amsterdam to New York. So then the distance is given. But the same problem is basically saying, okay, if the distance is given, I want to fly with the least amount of fuel. Because that's the same thing as saying with a given amount of fuel, I want to fly as far as I can. So this is the problem we're going to look at. Now there's a parameter you can define, and that is called specific range, airspeed divided by fuel flow. And fuel flow is usually expressed in newtons per second. So an amount of fuel per second that is being burned. Now, question is, why would you define this strange ratio? You will see that directly if you look at the dimensions. So airspeed is meters per second you fly. Fuel flow is newtons per second, amount of fuel per second. So the seconds are divided out, so seconds on the top and on the bottom. This means that V over F is an indication for the number of meters you can fly with a given amount of fuel. So you can see straight away that if you optimize that variable, then you can fly the furthest you can with a certain amount of fuel. So this is something, if you want to fly as far as you can, or over a given distance with the minimum amount of fuel, then you must maximize the distance you can fly with 1 liter of fuel. So that's pretty straightforward, I should say. But let's have a look at how far a propeller aircraft can fly, and then I'll finalize the story with the first propeller aircraft that actually flew across the Atlantic and how they managed to do that. So this fuel flow of a propeller, if this is the propeller and you have some kind of a propulsion system, then there's a certain power delivered to this shaft around which the propeller rotates. So P brake is what we call shaft power, and this is delivered to the propeller. So it doesn't matter how it's delivered to the propeller, but it's delivered to the propeller. And the propeller actually accelerates air. So the power you have available is some kind of efficiency multiplied with the shaft power. Now the reason it's called PBR is because the term comes from brake power. In the old days they used to apply a brake to a shaft to measure how much power it delivers. So what we can say is, okay, fuel flow is some kind of a parameter multiplied with the shaft power. You can imagine the more shaft power you want, the more fuel flow you have. So there will be some kind of a variable, and it depends purely on your engine, that tells you how much fuel you're using depending on the shaft power. So combining that with this equation for power available, you can say, well, fuel flow is this fuel consumption parameter, Cp, multiplied with power available divided by the efficiency. Now, in this steady horizontal flight, we're trying to fly as far as we can. So thrust is equal to drag, or power available is equal to power required. We can say, okay, we have power available in the equation, so we can also say that's power required, because they must be the same. So that's aerodynamic drag multiplied with airspeed. So we have fuel flow now here, we have airspeed, and remember, V over F meters per Newton is what we try to maximize. So if we rewrite the equation, then we get V over F is this efficiency divided by this constant multiplied with 1 over the aerodynamic drag. Now this efficiency and this parameter Cp, in normal applications you can say, well, that's pretty much constant for all the airspeeds that we're interested in. So that means if you want to maximize V over F, then you would have to maximize 1 over the aerodynamic drag, which means you have to minimize the actual aerodynamic drag. So we want minimal aerodynamic drag, and that's pretty, that seems reasonable, because you can imagine you're flying quite efficiently if the drag of the aircraft is really low. Now, drag was also drag times lift divided by lift, which is drag over lift times weight, which is CD over CL times weight. So, saying minimum drag is the same as saying, okay, I want to have maximum lift over drag coefficient. Okay? Now, if you look in the diagram, then the bottom diagram is the drag curve, the aerodynamic drag curve. So if you take that point all the way at the bottom, where you have minimum drag, then that you can simply read here, okay, that's the airspeed I should fly with my aircraft to achieve maximum range. And in the power diagram, it's this point here. And one thing to note is that power is a force times velocity. So the airspeed at which you have minimum drag is not the same as the airspeed where power is minimal. And that's because basically by multiplying with speed you kind of tilt the whole curve. So the minimum point is not the same. So you can read straight away from the diagram what the minimum point is, and from there you can actually see, well, that is the speed I have to fly at in order to fly as far as I can. Interesting to see maybe is that this point over here is actually where if you draw a line from the origin, that's where you just hit the curve. Because power is drag multiplied with airspeed. So this curve is basically a measure for power divided by airspeed, which is drag times airspeed divided by airspeed, which is drag. So a line from the origin, if it just hits the curve, that's the same minimum point, just a mathematical thing. So you can read from the diagram, okay, if I have this aircraft, I have to fly at 140 kilometers per hour to get as far as I can. Now, you have one problem, which I'm not going to solve today. I'd rather tell you one story before I finish. Of course, you want to fly at a lift over drag coefficient, which is maximum. But you can't just say to somebody, please fly at the minimum drag condition. You can still hear me. So you have to calculate the actual airspeed that belongs to that condition. But let's do that next week. I just want to show you one story before I finish. Let me find the sheets. So this was the first propeller aircraft that actually flew from New York across the Atlantic Ocean. Back in those days, nobody's ever flown across the Atlantic. So they had a prize. You could win something like $20,000 if you would complete the flight. The flight was from New York to Europe because of the wind conditions. Wind is always in that direction, so you have wind in the back and that helps you. And this guy, Charles Lindbergh, was the first one to complete this flight. And as you can see, he has a propeller aircraft. And what you can imagine, I've talked about specific range, but of course you want to take as much fuel on board as you can. Because this was all about flying as far as you can with a certain amount of fuel. So this whole thing here in the middle, that's all fuel tank. Now the guy is sitting over here. So he doesn't have a window. He has a small periscope to look outside in order to be able to fly. Now all looks very exciting, but it was quite serious business because before he took off from New York, Actually, several other people tried to do this, and because they loaded up their planes with a lot of fuel to be able to get as far as they can. The plane was very heavy, so quite a few of them actually weren't able to take off by the end of the runway and crashed. Other people were never seen again when they were flying over the Atlantic. So this was quite a brave thing to do, but in the end he managed to do so. And this is a plot I've taken from a NACA technical note. That's the predecessor of NASA. And what you see here this is basically the power required. So this is one of these power curves, and the point, if you draw a line from the origin over there, that's the minimum drag condition. So this guy, he couldn't look outside, so all he was doing calculations on board to figure out how fast do you actually have to fly to be in the minimum drag condition. So he was doing constantly these calculations. Flight took in the order of 30 hours, I think. And one thing I'll treat later is that I've already shown you that, can you still hear me? That drag is a function of CD over CL multiplied with aircraft weight. So you can imagine as this aircraft is flying for hours and hours, it's starting to get lighter and lighter. So this curve, the drag curve and the power curve, actually changes a bit. How that exactly works, I'll tell you later. But this is basically the curve for a lower weight, which means that minimum drag condition is actually at a little bit lower speed. So even though he was already flying for 30 hours, he had to decrease speed, and by the end he managed to reach the final destination, and he won the prize, and the rest of the story you know. So that's all for today. Next time I'll show you the actual calculation, and we'll start looking at endurance and speed stability.
Please visit our OpenCourseware website for more information. See you at our next